Meanwhile, on planet Watsonian, holographic character mapping in the evolutionary context of matrix encryption by Watson Williams, sole owner of 777 Technologies and the matrix encryption patent. Recommended prequel videos are as follows, and we have created a playlist containing them located in the description. We're pleased to announce that the originally patented version of matrix encryption with desktop graphical user interface is now available for free download at matrixencryption.com, a $40 value. To access your free download, just create an account, log in, and go to the products page, scroll down and click the free download. Choose a location and your download should complete momentarily. The package is 20 megabytes. If you do try out the originally patented version, and if you were as familiar as I am with the subsequent upgrades, you would see that it's usable but with limited strength and capabilities. How limited? Come, let me show you. Major historic updates. These are the post-patent updates, not including any minor updates or web updates. So the major aim of this presentation is to explain holographic character mapping in the evolutionary context of matrix encryption. And to that end, we're just going to take a moment here and briefly paint a picture of the pivotal updates that have happened since filing our patent. If you remember nothing else, just keep in mind that there have been 6 historic updates since filing the patent. So, algebraic substitution. The core discrete functions originally used a set of secondary functions, but these have been absorbed into the parent functions using algebraic substitution. This makes the algorithm a bit faster. Custom on-site auto-trimming. The original algorithm called for the key to have a length equal to the length of the encoded data. This is still the case, but with COAT, the tedium of having to enter a key of a precise length is eliminated as the large master keys are tapered automatically to the required length. This cancels any need to use a key set as defined in the patent of keys of various lengths. Key sets were cumbersome and took up lots of storage space and RAM, but thankfully COAT logic and the use of master keys presents a catch-all solution for any required key length up to the length of the master key provided, of course. Custom codex configuration. In my patent application, I briefly mentioned the possibility of using other codices besides the factory codex disclosed in my patent. But it wasn't until some time later that I coded the logic allowing for the use of user-customized codices. CCC increases the brute force resilience of matrix encryption by about 81 factorial. First character mastery. Originally, we needed the key to be less than the complement of the encoded data to prevent the emergence of an additional significant digit when adding the encoded data and the key. But as the depth of our understanding grew, we were able to conceive and map out all the possible scenarios an extra digit can cause during decryption. And we coded a logic tree that handles them all, and we call it FCM. Codex 90. In the beginning, we devised for the Codex to have 81 available assignments. Codex 90 is an improvement, but not the end of the story on Codex optimization. And as for file encryption, finally, matrix encryption was originally a plaintext-only algorithm. That's just how we thought of it. But we have since expanded the logic and the options on desktop to include the ability to encrypt files, with auto file type recognition coming in a near future update. Now that we have a high-level introductory conceptual understanding of the major historic updates, we present our currently highest functional form of matrix encryption available for purchase on the web app. Fox Essentials version 5 only lacks Codex 90 and file encryption and has no GUI, but it is packed with all the other previously mentioned updates for only $79.95. The post-PowerPoint updates. The PPP Updates refers to our most recent updates that have arisen since we began using PowerPoint to make videos. The increase in video quality and the clearer presentation of our ideas and claims allowed us to better see where there was room for improvement, sort of a mirror effect even without feedback from viewers. So, as of this production, there are 4 PPP updates, and the first one is the use of the floor division operator in place of the floating identity logic. This makes decryptions much faster than before, and you can learn more about this particular update in our most recent video titled An Unexpected Upgrade. Secondly, holographic character mapping, our premier PPP update, which we're unveiling gradually in this presentation. Thirdly, an update that in retrospect was perhaps too long in coming, but which is sure to be appreciated, automatic key and codex generation logic. Now users don't have to be bothered with finding and constructing keys and codices, but can do so at the click of a few buttons. And we'll be showing you how to do that during the HCM demonstration at the end of the video. Finally, another idea we've had recently, as we were saying, is to offer our originally patented version for free. So again, we invite you to download it and try it out in relation and in contrast to the information contained in this presentation. So again, having seen the prereq videos would be nice, but in case you haven't, in our video, The Most Powerful Encryption in the World, we calculated and compared that matrix encryption has achieved unprecedented levels of brute force resilience. We also disclosed a structural weakness in matrix encryption and how overcoming this would be the final frontier of matrix encryption, at least in terms of foreseeable core algorithm capability. What is the structural weakness? Strap yourselves in for a deep dive because in the end, it will make HCM seem almost intuitive. The subtle structural weakness is not really in matrix encryption itself, but rather emerges externally as a standard character operating system limitation. There are less than 100 unique standard characters on the keyboard, which leaves an assignment gap in the 2-digit character map. And this manifests as wrong keys and/or codices producing decrypted data that is obviously wrong because it is too short, less than half the length of the encrypted data. Normally, the original data and the encrypted data have this simple 2x deterministic relationship. We know how long the encryption will be, and if we try to recover the data with a codex and key, but it comes back shorter than expected, we can be sure the key and/or codex were incorrect. how data comes back too short. First, data is encrypted. A wrong key and codex are applied to the encryption. This produces an incorrect encoding during decryption. The incorrect encoding likely contains vacant two-digit assignments. The decoding process then results in data too short because the vacant assignments do not map back to any characters in the codex and are skipped. The number of theoretically vacant character to two-digit assignments is 100, running from 00 up to 99. But including spacebar, there are only 95 standard 1-byte characters on the keyboard, leaving 5 theoretically vacant assignments, and clearly indicating that the character map can't be classically completed. Now the actual number of vacant assignments, as it turns out, technically depends on the codex configuration and whether the codex is submitted through a text file or is hard-coded, because some characters resist hard coding. But to keep things moving along, the basic idea is that we have two codex configurations. The classic Codex 81 with 19 vacant assignments running from 00 up to 09 and 10, 20, 30 up to 90. And Codex 90 with only 10 vacant assignments running from 00 up to 09. Codex 81 was our naive original codex configuration, whereas Codex 90 was basically the half-baked attempt to solve the problem of vacant assignments after I began to understand the structural resilience problem they pose. With Codex 90, we were able to cut the number of vacant assignments by 9, down from 19 to 10. Very little algorithmic change was needed here, together with the acceptance of a 10% chance of losing the very last character in plain text, due to minor edge case non-injectivity for the CBD counting procedure, occurring for 9 out of 90 elements, 10, 20, 30, up to 90. Remember, injectivity means a unique output for every input. So if n ends in 0, we have that the f of n equals m, but then also the f of n minus 1 equals m. n minus 1 ends in 9, of course, but what about the f inverse of m? There are two possibilities, which leads to data loss. Conceptually, what happens is that you'll have some data. It will be correctly encrypted and decrypted. The initial and final lengths will be equal, but the last character is no longer equivalent with its initial value. LCL is a reasonable trade-off, especially considering the concept of padding we've talked about before, which is the voluntary adding of irrelevant characters anywhere, but particularly after relevant data, to offset the potential for an acceptable level of data loss with Codex 90. This complements layered encryptions because, remember, pure gibberish is actually plausible data if it's the right length. We can encrypt AES encryptions with Codex 81 or with Codex 90, provided we're cognizant of our last character assignments so as to manually avoid that 10% chance of LCL, which would corrupt an AES decryption. And so we're building a smarter, more elusive algorithm, but even if layering is assumed, wrong keys and codices are still obviously wrong if the decryption is too short, and that key codex combo can be eliminated by an attacker. So how can we make keys and codices impossible to eliminate based on decryption length if there aren't enough standard characters to complete the character map?
There he is. Where? There. We have the holy hand grenade.
Yes, of course. The holy hand grenade of Antioch. 'Tis one of the sacred relics Brother Maynard carries with him. Brother Maynard, bring up the holy hand grenade.
Holographic character mapping lets you choose an arbitrary number n from 1 through 10 for Codex 90 and 1 through 19 for Codex 81. N unique characters are then randomly selected from the user-submitted codex. N unique vacant two-digit assignments are randomly selected. A holographic map is constructed from the N codex characters to the N vacant two-digit assignments, a double-blind process. Any characters in the plaintext to be encrypted that were randomly selected receive a holographic mapping assignment during encoding. So the way it will look is that, say we're using Codex 81, for instance, and we choose 3 characters for the hologram. 3 characters are then randomly selected from the codex you provided and are mapped to 3 randomly selected vacant 2-digit assignments. Anywhere these characters appear in the text to be encrypted, these holographic values are mapped directly behind the normal assignment. If the codex calls for A corresponds to 21, then everywhere A appears in the plain text, the hologram causes A to be translated as 2120 in the encoding. Thus, the encryption becomes chaotically longer than twice the length of the original message. It's now impossible to deduce the original message length from the encryption length, as this would require prior knowledge of the original message contents and how they were randomly mapped. Get it? Key Codex Combos can no longer be discarded or ruled out simply for producing results less than half the length of the encryption, and this uncertainty quickly extends into the hundreds and thousands of digits and beyond. Holographic character mapping increases resilience in the afterglow because the key must be correspondingly longer to account for the holographic characters. But more importantly, the main goal achieved is total structural ambiguity, meaning there are no structural weaknesses in the matrix encryption algorithm to exploit. Otherwise, prove me wrong, and brute force is the only reasonable course of action for third parties. Make a wish. The beauty of HCM is that the vacant assignments that were once a weakness have become a strength. Their values don't even have to be known, and they naturally collapse like a wave function when the proper Key Codex combo is applied. Holographic character mapping is really a triple-blind entropy injection system that makes knowing the correct Key Codex combo a non-deterministic prospect. You don't know how many characters were selected for the holographic map. You don't know which 2-digit vacant assignments those characters were mapped to, and you certainly don't know how many times those selected characters appear in the original text. How will you set a lower bound on how long the data should be? You're lost inside a holographic matrix. Matrix encryption is moving into the heroic phase. I hope you're ready. Welcome to the Holographic Character Mapping Encryption Demonstration. We'll start by launching the program and adjusting the layout. There's probably a way to make that happen automatically. The program is console-based and some relevant information will appear there. We need to enter the contract key. In this case, it's just test. We'll select register and enter a desired username. Check availability. If the name's available, we then enter a password. Now we'll create a randomized custom codex and key. Enter a name for the codex and choose Codex 81. And there's our new codex. Blow it up a little bit so you can see it more clearly. It's 81 characters. Let's create a new master key and enter the desired number of digits. And we'll go with 75,000. Okay, and it automatically opens the master key file. Scroll down to the bottom and show that it is in fact 75,000 digits long. We'll leave that open and log in with our new account. Select plaintext service, Codex 81. We'll use our personal codex and initiate holographic character mapping. As explained before, Codex 81 has 19 vacant assignments, so we can choose a number from 1 through 19. We'll choose 19. Any number outside of that doesn't work. Now we need something to encrypt. We'll use this text file composed of 25,000 characters and named 25,000. As we can see, instead of needing a key with 50,000 digits, because of HCM, the key needs to be 57,422 digits, and our master key is up to the task. Encryption complete. We'll save to a custom file, 25,000E for encryption. And let's open the file and check that the encryption is also 57,422 digits long. It is. Now we just need to run the decryption program to recover the data. So let's exit and launch the decryption program. Ooh. Fix the window. Okay. Contract key, log in. We don't need to register in this case because we have the codex and the key. So log in and go back to plaintext, Codex 81. We need to use the say in codex, but we can submit it through the custom portal. Okay. And the file to decrypt is, of course, 25,000E. Decrypt it. We need the key, the Saiyan master key. Upload it. And the decryption is done almost instantly, as this version uses the floor division operator rather than the floating identity logic. Save the file to 25,000D for decryption, and lastly, take a look at it side by side to confirm that it's identical to the original message. And it is. So the encryption with holographic character mapping worked, and the holographic digits disappeared with the correct codex and key perfectly collapsing back to the original message.